A paper from about 2 years ago is suddenly getting a lot more attention, and it relates to the leak from last November about OpenAI's Q-star and now what they're apparently calling Strawberry. And interestingly enough, it has star in the name, so combined with Q learning, it actually might be Q-star itself. Let's take a look. Hey y'all, it's Dr. Know-It-All. I'm going to talk about this paper from Seligman et al. Today. Really interesting paper. You can see it's from May of 2022, so just about 2 years ago. But recently it's really bubbled up to the forefront in the popular AI space, in other words, YouTube channels and things like that. And the rumors have it related to OpenAI's Q-star, which is now apparently known as Strawberry. And tangentially, this relates to what Elon Musk said a while back about if you told an artificial superintelligence that what you wanted was lots and lots of strawberries, what it would do is destroy the entire universe and make strawberry fields forever. So reference back to the Beatles, a reference to Elon Musk, and apparently as well a reference to Q-star. I'm also going to show about a 3.5-minute section of a video that I did last November, right around the time the original Q-star rumors started leaking and Sam Altman got fired from OpenAI and then was rehired, all that stuff. So anyway, all of this stuff all relates together. First, I'm going to go through this STAR, Self-Taught Reasoner, or STAR, Bootstrapping Reasoning with Reasoning paper, and I'm going to go through in some detail here. I'm going to skip a lot of sections and everything. Of course, I will leave a link to the archive paper in the description, so you can check it all out to your heart's content if you want to geek out on it a little more. So first, let's start with the abstract. Generating step-by-step chain of thought rationales improves language model performance on complex reasoning tasks like mathematics or common sense question answering. And absolutely, this is true. Interestingly enough, it was also true 2 years ago. So while things have changed in that regard, you have these people who were at Stanford and Google DeepMind who clearly understood where things were going. Anyway, it says, we propose a technique to iteratively leverage a small number of rationale examples and a large data set without rationales to bootstrap the ability to perform successively more complex reasoning. This technique, the self-taught reasoner, or STAR, relies on a simple loop. Generate rationales to answer many questions, prompted with a few rationale examples. If the generated answers are wrong, try again to generate a rationale given the correct answer. Fine-tune on all the rationales that ultimately yielded correct answers and repeat. So that's what we're going to discuss in this video here, right? That's a lot of stuff to get through. It actually is relatively straightforward when you really understand it, and I think this paper is actually very well written. So good job, folks, on writing a very good paper. Anyway, the last highlighted part of the abstract here is it performs comparably to fine-tuning a 30 times larger state-of-the-art language model on common sense QA. So what that means is you could take a 10 billion parameter model and it should perform approximately as well as a 300 billion parameter model. So this means you can shrink down a lot of the reasoning into a very small form factor. The interesting part for OpenAI, of course, is that they wouldn't necessarily have to shrink this stuff down. What they could have done is use something like STAR plus Q-learning, which I'll talk about a little bit later. They could have combined that in a frontier model, in other words, a large multi-hundred billion or multiple trillion parameter model to create GPT-5. And so they could have taken this idea and really run with it, and they might have something pretty remarkable for us coming up potentially after the presidential elections in the United States. And I'm not going to get into that today, but that was it was quite a weekend that we had. Anyway, don't want to talk about that today. I want to talk about much more positive things here. In the introduction, we have human decision-making is often the result of an extended chain of thought, which is completely reasonable if you think about that. Then they note that generating explicit rationales before giving a final answer or rationale generation is valuable for large language models across diverse tasks, including mathematical reasoning, common sense reasoning, code valuation, etc. So they talk about what's available today or 2 years ago or whatever. You can create a fine-tuning data set of rationales that is difficult to scale, or you can do a template-based method that relies on automatically generated rationales, but they only work when a general solution is already known to us, right? So that we can tell it what the general solution is already. Of course, both of those have significant problems. So that's where we get to what STAR is, and I'm going to get back to this figure in just a little bit, but first I want to talk more through the paper so that the figure makes more sense. So they say here, by leveraging the large language model's pre-existing reasoning ability, we iteratively bootstrap the ability to generate high-quality rationales. Specifically, we few-shot prompt a large language model to self-generate rationales and refine the model's ability further by fine-tuning on those rationales that lead to correct answers. We repeat this procedure using the improved model to generate the next training set each time. This is a synergistic process where improvements in rationale generation improve the training data, and improvements in training data further improve rationale generation. So if we go back to this figure, you can see this is the top part of this figure. What you've got is you've got a question and an answer. You're giving it a data data set where you know the question and you know the answer. The red part is what you're asking this LLM to generate, which is a rationale, which is like, why did you come up with this answer? So you give it a question, the large language model generates something, it gives you a rationale, so it inputs that red part, and if it's correct, it goes back in here and it creates a bigger data set for it to train on. So this is a way of synthetically generating more and more and more data without having to have humans in the loop, and that's a really important part of what Q-star supposedly is. It's the ability for AI to self-improve. So you can see over on the right, you've got the question, what can be used to carry a small dog? And then, obviously the answer is basket down there. But what this LLM is tasked to do is the A part, right? That red part there. The answer must be something that can be used to carry a small animal. Baskets are designed to hold things, therefore the answer is basket. The answer is B, and then you feed that into the data set. So you've got this rationale now that is part of this new data set. So what you do to train this part of the system is you give it a small collection. I don't know if they had 100 or 50 or something like that. You give it a bunch of these things with the rationale built in, right? You have a human being write that part of it. You give it to the system, and then you feed new questions in where you know the right answer. When it gets the right answer, you take that rationale, you put it in as if a human being had written it, and you augment the data set, and you keep building out and building out and building out the data set. And so you don't need a human being to build all of this data, and humans are very expensive and very slow. So this is a great way to take things out. Of course, your question is now, well, what if it gets it wrong? What if it doesn't get the right answer? That's where the bottom part of this figure comes in, but let's read about that first. However, we find this loop eventually fails to solve any new problems in the training set because it receives no direct training signal for problems it fails to solve. Pretty obvious when you think about that. To overcome this issue, we propose rationalization. For each problem that the model fails to answer correctly, we generate a new rationale by providing the model with the correct answer or a hint. This lets the model reason backward. Given the correct answer, the model can more easily generate a useful rationale. These rationales are then collected as part of the training data, which often improves overall accuracy. So if we go up here to this figure, you can now look at the bottom part, right? So you ask the large language model a question, what can be used to carry a small dog? Let's say it gets this wrong. The LLM generates a rationale for the answer and the answer, but it gets the answer wrong. So now that's not included in this top loop. But what it does instead is it goes to this bottom part of the loop where it's wrong answer. Star gives it a hint, and in this case, the hint is just B is the correct answer, right? It would put a little thing after basket and say this is correct or correct answer or something like that. That's the hint. Then you feed that back into the large language model and say, now with the hint, can you do this? It then has the ability to know the answer and work backwards to create the rationale. And then assuming that that is correct, it then feeds that into the new database and augments the data. Now they don't state what they do if this continues to get it wrong, and maybe they just throw that out. I'm not exactly sure. But assuming that it gets it right with the answer, and it sounds like most of the time it does, you can then feed that back into the data set as well. So now whether it's right or wrong, it can still learn on this data, and that is incredibly helpful. So this means that the data set, whatever the data set it is, whether it's coding or mathematics or just, logic or something like that, you have to have the question and the answer, but you don't have to have that long thing in the middle. You don't have to actually have the rationale because you can bootstrap the ability for it to build its own rationale. And that means that you can synthetically augment the data over and over again, which again means that this thing can train itself. It doesn't need humans in the loop anymore to improve itself. So you can see they say that here. It's a scalable bootstrapping method. It means you can start with a very small number of these things actually created, and you can bootstrap it, and it'll just keep building itself up so it can generalize on that. And that means it's able to effectively translate a small number of few-shot prompts into a large rationale data set, yielding dramatic performance improvements. So they say they make the following contributions. We propose a bootstrapping mechanism to iteratively generate rationale data set from a few initial examples with rationales. We complement rationale generalization, in other words, when it gets it right, with rationalization, which is when it gets it wrong and they give it a hint, where a model is tasked with justifying an answer and then fine-tuned as if it had come up with the rationale without any hint. And then the real crux of this for OpenAI and for us looking at this is we propose what is, to our knowledge, the first technique to allow a pre-trained large language model to iteratively use its language modeling capacity to improve itself. So in other words, it's able to improve on its own. This is kind of the North Star that OpenAI has talked about and many, many other companies. In order to get to AGI and in order to get to artificial superintelligence or ASI eventually, you need these to be able to train on their own, and you need to get rid of reinforcement learning through human feedback because humans will eventually fail. An artificial superintelligence by definition has to be smarter than people, and in order for it to be smarter than people, it's going to have to train on data that human beings couldn't even generate themselves because we're not smart enough to generate them. So it's a weird little conundrum that you get in, similar to AlphaZero that DeepMind came up with, where you had agents that played against each other in games and just worked on their own. They knew the rules of Go and that was all they knew. And they, in very short order, became better than the best human beings by a significant margin. So that's what you're looking at here, is that ability to learn on its own. Yes, it's kind of terrifying when you think about that, but it's also the direction that you have to go in order to get to artificial superintelligence. So then they break their methodology into two things: star without rationalization. In other words, when it gets the answer correct, you can see what they do there. And then they add rationalization here. Since the model is only trained, and this is without rationalization, is only trained on the examples which it answers correctly, improvement ends when the model fails to solve new problems in the training set. So their way of fixing this is giving it a hint, and here is the hint. You can see, grocery cart is the correct answer. And now what you're doing is you're saying, hey, correct. This one, you're saying, look over here. This is the right answer, which gives the large language model the ability to hone in on the correct answer and to understand that's the correct answer and generate, ostensibly, a better rationalization for that answer. And then that's fed back into the data. That new data is used to fine-tune the model further. Interestingly enough, they say that they don't fine-tune the model and keep fine-tuning it. They go back to the original version of the model with every one of these data augmentation steps so that they don't overfit to the data. I don't know that OpenAI and people in the future, since 2022, will have done that. They may have decided to just keep iterating on the model as well. So what they're talking about with STAR is that they keep making the data set bigger and bigger and more robust and better, but they don't make the model better. They just go back to square one. They take the original model and retrain it with the better data. And this makes sense for a relatively small model. They're using GPT-J, which was a very small model, and it's a couple of years old. So, it could easily overfit. But if you're talking about a multi-trillion parameter model, it probably doesn't care. It's going to be okay and not overfit if you continue to take the model. So this is something that they could definitely do, is that they could improve the data set, then they can take that improved model and they can use that to generate more data, improve the data set, improve the model, improve the data set, improve the model. That's not part of this paper, but definitely something that OpenAI and others might be working on right now. So quickly, you can see GPT-J, which was only a 6 billion parameter model, relatively small, even at that point, relative to frontier models. But they were able to get it to perform very, very excellently compared to even the frontier models at the time. This figure is worth pointing out. They did a really bad job of explaining it, but I think I've got it figured out at this point. This is adding two digits together. The red line is adding two single-digit numbers together, like 2 plus 3. The yellow line, I believe, is two-digit numbers, like 25 plus 13. The green is 3-digit numbers, the blue is 4-digit numbers, and the purple is 5 digits. So it takes a lot of time for it to figure out how to do this, especially without rationalization. In other words, without that incorrect loop. And you can see how much faster it is at getting better. Unfortunately, they changed the scale in these two graphs, so it's not a good comparison. So 16 is right here. And that is, you can see that the blue and the green and the purple haven't even started by 16 epochs. They haven't begun to learn to figure out how to do a better job. But by 16, they're all in the 70 to 100% range. So unfortunately, what they should have done is kept both of them at 28 so you could see comparatively how they did that. But just understand that these learn much, much faster, especially the 2-digit one. It's like, boom, it gets up there really, really quick. So that's pretty cool to see. So now let's jump down to the discussion and challenges. The impact of rationalization, which is, again, when it gets it wrong, telling it about that. Rationalization allows a model to reverse engineer a solution or provides a heuristic for identifying whether each step makes the conclusion more likely. Notice the fact we've got the word heuristic in here. We're going to get back to that when we talk about Q-learning in just a second. And notice they also say this parallels real-world problems where the final result is known but challenging to derive a good justification. And that would be kind of like an NP-hard sort of problem. It's the kind of thing where checking that the answer is correct is relatively easy, but figuring out the answer is very difficult. So I think that's just interesting how you can leverage the ability to be able to check an answer quickly and easily versus a difficult time trying to figure out what that answer actually is. And then putting this a little more specifically, rationalization conditions on the answer, letting us access an alternative distribution, which may be a better search space for the rationales. And this allows it to do off-policy estimations for the objective. And interesting, they talk about reinforcement learning objectives and things like that as well. And then they discuss things like temperature and few-shot prompting as well, but I'm going to skip down to the conclusion, we present the self-taught reasoner, or STAR, which iteratively improves a model's ability to generate rationales to solve problems, and in order for the first iteration of STAR to succeed, few-shot performance must be above chance, implying that the initial model must be big enough to have some reasoning capabilities. So in other words, you can't have a super small model. It's got to be big enough to begin to reason, but then after that, it can bootstrap itself up and get better and better. So really interesting. They say GPT-2 was not capable of doing this, which is interesting. It means that you need a GPT-3 sort of baseline in order to be able to get up to speed and begin to learn. So there needs to be some ability for the large language model to rationalize and be reasonable, but after you get that point, you can bootstrap it on its own. So with that in mind, I'm going to play a little section of a video I did back in November that discusses deep Q networks, and I think that, STAR and deep Q networks really connect together in the area of heuristics specifically. So let's take a listen. Hey y'all, it's Dr. Know-It-All. I am going to start very quickly by taking a quick dive into Q-star once again. I know I just talked about it. I'm going to have to do another video on it once I've had a chance to digest this more, but this is really interesting. Stephen McAleer, I believe is how you pronounce his last name, said, "We invented Q-star first." So as is not surprising at all, there are always researchers out there from UC Irvine and the University of South Carolina who worked on something called Q-star, and this relates back to A-star. I'm actually going to look at A-star first. A-star is an algorithm that's been around for machine learning for forever, and like I said in yesterday's video, you probably are using a variant of it when you do a Google Maps search or something. It's a way of finding out the least cost way of getting from one place to another, and that could be physically, like in maps things, or it could be more along the lines of a least cost type of path through a game or through some sort of economic turmoil, whatever. You can define it the way you want to, but essentially it depends on heuristics. So human beings come up with a cost function. In other words, this little red guy is trying to get to this green guy, and if it hits a black thing, that's like a major cost, right? So that's like, it's impossible to go through there. But what you want to do is find out the most efficient way to get from the red dot to the green dot. And so with A-star, you define the cost of moving your little marker, whatever it is, like this red guy, from here to here or here to here or something along those lines. So you define that cost, and then you create a metric that tells you how far apart these things are. In this case, it's pretty obvious. You could say, what is the linear distance between these two things? Or you could do what's called a Manhattan distance, which is basically how many squares apart are you. Anyway, this is up to humans to decide. Humans come up with heuristics that define the cost of every single move and how far apart these things are in some sort of solution space. And A-star utilizes that to determine what the best path forward is to get from your beginning point to your ending point. And so that brings us to Augustinelli et al.'s paper here, A-star search without expansions, learning heuristic functions with deep Q networks. So this is really interesting because heuristics and deep neural networks have generally been at odds with each other. And this is a way of trying to recombine them. And I think probably a very good idea. And obviously, if OpenAI has taken this and run with it and has come up with something that might be AGI, or at least closer to that, it obviously has some advantages. So with a neural network, the traditional way to do it is you get rid of heuristics, you get rid of human knowledge, you just feed data to the neural network, and you just say, here's all this data, you figure out what's going on. The basic idea here is that it sounds like what they've done is that they've utilized a combination of heuristics and the traditional deep neural networks in order to get something that functions more rapidly, is more compute efficient, and can come up with better solutions quicker than the older version. So by all means, feel free to, pause this video and look at the abstract if you want to, but I'm just going to turn to the last couple sentences here. Furthermore, Q-star search is up to 129 times faster and generates up to 1,288 times fewer nodes than A-star search, which means it's better than a traditional heuristic search, which is reasonable because that's the whole reason why we use neural networks and stuff. And then finally, although obtaining admissible heuristic functions from deep neural networks is an ongoing area of research, in other words, it's an unsolved problem, if you can figure that stuff out, they prove that Q-star search is guaranteed to find a shortest path given a heuristic function that neither overestimates the cost of the shortest path, in other words, from place to place, nor underestimates the transition cost, in other words, from one square to another. So that's a pretty impressive statement and proof, and this is really interesting stuff. I've been very interested in the combination of heuristics and deep neural networks myself, but had not come across this before, so super cool, and thanks to to Adrian Dittman for pointing this out, because I would not have seen it otherwise. So anyway, like I said, I'm going to digest this further and do another video that completely goes into this in more detail, but I thought it was worth bringing up since it's part of this conversation and could be leading OpenAI to believing that they're very, very close to artificial general intelligence. All right, so that's what I had last fall. You can see this paper. It didn't have the date on it before, so I'll bring it up right here. You can see it's from March of 2023, so year and a half-ish old or something like that. So we had STAR that's a little over 2 years old. We have this one that's, you know, a year and 5 or 6 months old, whatever the amount is. Anyway, you've got these two papers that I think OpenAI and potentially others have kind of combined into what became QStar. And QStar then, I don't know if it was just because the name became popularized and they're like, we need a new code name or something, but now apparently it's called Strawberry and not QStar. But while this is obviously speculation on my part and many other people's part, so I'm not the only one saying this, the likelihood is that we've got some sort of combination of STAR plus this DeepQ network STAR version. And the important part about DeepQ networks is they expand upon A-star search. And A-star search, again, is a classic algorithm in machine learning, and it's still used to this day. And it's actually a very important and very powerful algorithm. But in order to use it, you need to know the search space. And in other words, you need to have kind of perfect knowledge as you expand out, at least as it kind of grows and hits the frontiers of where it's searching for. It needs to be able to see what's going on with pretty much perfect knowledge. But then you also need a path cost heuristic and also a heuristic for the estimated total distance to the solution. And while that's pretty easy to figure out with that figure that I showed, where it's just like, you know, how far is it from here to here or something, and how do I get there the most efficient way, that's relatively easy. In any kind of real world problem, like full self-driving or something along those lines, like what Tesla does, the issues are that figuring out those heuristics is very, very challenging. And so what you do is, instead of a human trying to figure it out, you actually let machine learning try to figure it out. And that is what these DeepQ networks are really good at doing. So that's really amazing. You can have the deep learning architecture, you can have the neural network figure out the best heuristics for both the path cost and the estimated cost to get to the solution from the current state where you're in. And that proves to be significantly better than humans just trying to figure it out on their own. But then what we can do is we can actually combine this with STAR, with the self-taught reasoner, because you can use the heuristics to figure out the best way to condition this to create new rationales, which then allows it to grow the data set and actually train on a new, better data set without human beings in the loop. So a combination of Q and STAR, which would obviously be QStar, which again is what it sounds like OpenAI was originally calling this before they changed the name, again, probably to hide it more effectively from us normal people. You get a combination of Q and STAR, and it makes perfect sense that these two things would be thrown together with the potential of not just holding the model in place and retraining it from scratch every time you have your new data set, but also bootstrapping the model as well as you're doing this. So you have the ability to bootstrap your heuristics, bootstrap your model, and bootstrap your data set. You can bootstrap all three of these at the same time, and that can be done without human intervention, which, if you get to that point, a computer is really, really good at training itself because it's way faster than we humans are. And that's the exact sort of situation that could lead to this artificial general intelligence. It could lead to something that's able to reason. It could behave like an agent. It could have powerful reasoning capabilities, which is something that traditional large language models are really, really bad at. But this really could have opened the floodgates. And this is something that OpenAI may have gotten really good initial results. We don't know exactly why they haven't produced something on the order of GPT-5 at this point, but maybe that's because it's such a significant improvement over GPT-4 that they want to sort of roll it out slowly, and they want to make sure that they don't scare the public with how good it is. So we will see. The other option is that things have really, really slowed down, because that is another theory that's going around right now, is that frontier models have really stalled out and it costs way too much money to train them, and they've stopped getting better. And so we could be approaching another AI winter, or at least an AI fall or something along those lines. I'm going to do a whole other video on that soon, I hope. But if this methodology of combining Q and STAR together are able to overcome the reasoning problem, that could boost us into another AI hyper summer instead of summer. We could have global warming on the AI front, I guess. All right, so that's what I've got for you all today. Let me know in the comments what you think about this, if you have other insights or other rumors that you've heard. And while you're down there, if you don't mind liking and subscribing, it really helps out the channel. Thank you all so much for doing that. And in the meantime, I will see you in the next video. Bye-bye.